So let's start the second session of the morning morning second talk. The speaker is Professor Dipendra Prasad from IIT Bombay. The title is An Introduction to the GGP Conjecture. Please.
All right. Thank you. Yeah, good. So I will continue my lecture from last time. I guess almost everyone here today has attended the lecture, though there might be a few new people. Yesterday, I discussed the general notion of branching law and emphasized multiplicity-1 theorems, which are often proved via a method of Gelfand, which works in many situations, but I am not certain it works in all possible situations. It's a very useful way of proving multiplicity-1 theorems. I want to emphasize the role of multiplicity-1 theorems in relating global period integrals to what one may call local period integrals. So last time, at the end of the lecture, I was in the context of automorphic representations of a reductive group. You know, most of the time I will be quite elementary, but for the moment, these are automorphic representations on a reductive group. And one defines the period integral P. It's a linear mapping from pi to C. And its period integral on a subgroup H by sending a function f to integral f dh over HA mod HF. And this is an HA invariant linear form. And we are in the context when G comma H is a Gelfand pair. So there is a uniqueness of invariant form, which we assume is unique up to scaling. And I said that because this is a HA invariant linear form, if this has to be non-zero, then locally there should be HFV invariant linear form. So if pH is non-zero, then one must have all the representations phi v, then all the representations phi v must have HV invariant linear forms. HFV invariant. And one of the GGP conjectures in the global context says that conversely, if pi is equal to tensor product of phi v with phi v HV with pi v carrying HV invariant linear forms, invariant forms, then this period integral pH is not identically 0 if and only if some central critical value that we will come to is non-zero. Yeah.
The target is one dimension.
Uh-huh.
So the huge kernel we have.
Yeah.
That means you basically have a unique cusp of F, which is going to zero up to scale zero.
No, meaning one can think it differently. You know, you have infinite dimensional space and a subspace of codimension 1, but a subspace of codimension 1 is negligible. So if you take any random vector, it is not in the kernel. So one should not say that only one vector goes to non-zero, but rather all vectors go to non-zero because it's a codimension 1 subspace. Yeah, I mean, yeah. All right. So what I want to begin today is by relating, yeah.
L half might have more arithmetical meaning like a Birch and Swinnerton-Dyer.
Yeah. No, so I am coming to a bit of that. Yeah. So I wish to relate this global period integral to certain local period integrals. Sorry? Yeah, I mean, you know, this group itself in the notation of the previous lecture is G cross H. And H is the diagonal one. But in fact, for the moment, I will write G and H will be the subgroup. So I will not write G cross H. This G is G cross H of yesterday. Okay, so this is a rather brilliant idea of Ichino and Ikeda. And I mean, usually it goes as Ichino Ikeda's refinement of GGP. And what they do is that, you know, if you are given local representations pi v of the group GV, then the local uniqueness theorem say that it has a unique invariant linear form, but which is a bit, which is quite a bit abstract object. But one can construct a, so this is what is called doubling of the variable, and one can double the representation pi v, and instead of constructing a HV invariant linear form on pi v, one can construct a HV cross HV invariant form on the tensor product. And this is, so there is HV. Linear form, and this is constructed by, yeah, so this is constructed by sending a vector v1 and a vector v2 to, so for this I will assume that pi v is a unitary representation of the group GB, and one looks at HV1, v2, dH over HV. So since this is a unitary representation, this bilinear form is diagonal HV invariant. And because we are averaging it out on the first variable, it is also invariant under the first copy of HV, and therefore this is an HV cross HV linear form. So, of course, one will have to prove that this converges, and one also needs to prove that this is relevant for the question at hand. You know, you have created some HV cross HV invariant form. So that HV cross HV invariant form, if it is to be non-zero, then this pi v must carry an HV invariant form. But the converse is not obvious. This would be obvious in the context of finite groups where there is complete reducibility and so on. So there are two somehow quite non-obvious theorems which are brought to bear on this linear form. First is due to Walsh-Forget, which says that this bilinear form is not zero if and only if phi v carries an HV invariant form. And then the next one is due to Ichino-Ikeda. And they say that, okay, so I suppose this must come before A, this converges. So I am a bit confused. Maybe Walsh-Forget did it in some context, and this is, so this converges for pi v, a tempered representation. Yeah. Okay. So what one is going to do is to relate. So given the period integral pH, one can look at pH tensor pH bar. That is a mapping from pi tensor pi bar to C. Sorry?
It's the statement of convergence. B.
B is a statement about convergence, yeah.
So if it is not tempered, if it is albeit, you regard this linear form as non-zero?
No, I am a bit confused. As I said, one cannot talk about bilinear form being non-zero without its convergence. So Walsh-Forget must, you know, Walsh-Forget started doing some of these matters for supercuspidal representations. And for supercuspidal representations, the matrix coefficients are compactly supported, and therefore this would not have been an issue. So maybe he began this observation, and it was carried out in this generality by Ichino-Ikeda. But the convergence is due to Ichino-Ikeda. So we have this period integral. On the other hand, so to say, this one, we have created these invariant linear forms. Maybe I will call them MV. So this is called the matrix coefficient. And so we will have tensor product over V of this, and this is tensor product of MV. So, you know, given linear forms on pi v tensor pi v to C, you can look at their restricted tensor product and hope to construct a invariant form on the whole tensor product. For this, you need to ensure that on the spherical vector, the value taken is 1. So this is one of the main calculations which Ichino Ikeda did. MV at V0 comma V0 equals value of an L function, which is essentially L half of pi 1v tensor pi 2v. And one needs to notice here that where V0 is a spherical vector, with V0 comma V0 equals 1. So a spherical vector is unique only up to scaling. Once you demand that its norm is 1, V0 is unique up to modulus 1, whereas if you change V0 comma V0 by modulus 1, this inner product doesn't change. So this is well defined. This is a well-defined object, and MV, V0, V0, this doesn't depend on the choice of V0 with this scaling. And therefore, it is meaningful to say that these two are equal. So there is, this is one L function which appears. There are a few other L functions which appear, but this is the most important one. There is an explicit value given. So what Ichino Ikeda do is that instead of looking at this invariant linear form, they scale it out by dividing by this L value. So define MV star to be MV upon L half. I mean, as I said, there are a few other L values which are there, but I will not make a very precise statement. This L value is non-zero. These are tempered representation, and L half is non-zero. So now, sorry, for tempered representation, L values more than LS, S greater than 0 are non-zero. Meaning anyway, local L values are always non-zero, so you can divide. This is neither 0 nor pole. L values are, local L values are 1 upon something, so it is always non-zero, but it doesn't have a pole. So define MV star, and then it makes sense to define tensor product of MV star from pi v tensor pi v star to C, and this is tensor product over all V. Sorry? Yeah, pi v bar. And so now we have that global period integral on pi tensor pi bar, and we have these local integrals on tensor product of pi v star, and what Ichino Ikeda conjecture says. Conjecture says that this period integral pH tensor pH bar is equal to this MV tensor MV star, this tensor product over V. So, you know, these are invariant linear forms on the same representation, and these are unique, and therefore they must differ by a scalar. You know, these are invariant, and therefore they differ by a scalar. And so, you know, we have divided these local periods by L half. And what they propose is that it just needs to be divided, multiplied by, and perhaps there are a few spurious factors, and then there is a bit of a serious factor, cardinality of some component group, but something very precise. So this is the more precise version of the GGP, which says that if local invariant forms exist, and if the L value is non-zero, then the period integral is non-zero. Sorry? The denominator, I said, it is some cardinality of a global component group, which I am not yet defining. It will come up in due course. I think the point which I am making is that somehow the GGP conjectures are kind of not so useful arithmetically till you can relate them more precisely. And Ichino Ikeda have made it totally precise. But this is what is, so sometimes this is called doubling of variables. Oh, yeah. Okay. So there is one more normalization which one needs to worry about. You know, so I said that these local representations are unitary representation. They come equipped with a Hermitian form. But once again, the Hermitian forms are not unique. On the other hand, the global automorphic form has more or less a unique bilinear form, what is called the Peterson inner product. So one important normalization which one must fix is that the Peterson inner product, so this is the Peterson inner product, is equal to tensor product of local Hermitian forms. So, you know, doing this is not canonical. You can multiply at one place by 2 and divide by 2 in other place. So you can do, but this global equality is required, and that is all that is needed to make precise this relationship between the global period integral and the local period integral. I mean, yeah, so I mean, this space of functions that one is talking about, once you have the unitary structure on the representation, these are canonically defined functions, and the integral makes sense, and that defines your invariant linear form. So, in fact, in this normalization of the Peterson inner product as local one, so what one means is that if you have a global automorphic form F and G, then this is equal to FV GV when F is equal to tensor product of FV and G is equal to tensor product of GB. I mean, of course, one needs to worry about that in a global automorphic form is only isomorphic as a tensor product. There is nothing canonical about this, but you fix an identification. You fix an identification, and then you demand that the global period integral, the Peterson inner product is related to the local unitary structure by this formula. So no, I mean, this is rather beautiful formalism. It seems to relate the global period integral with local period integrals in a very precise way by saying that you have created two invariant forms on the global object and they differ by a scalar, and that scalar is nothing but the L value. So, you know, in fact, this is also the reason why in all the works on period integrals, it is not the period integral which appears, but it is the absolute value square of the period integral. Because we don't consider pH, but we consider pH tensor pH bar, which means that on a vector like f tensor f, it goes to integral f times integral f bar. And one is saying that integral f times integral f bar is related to certain local period integrals.
Why is doubling necessary?
Yeah, you know, Akshay Venkatesh has large papers to explain why doubling is necessary. Yeah, so, I mean, I think part of the deal is that, you know, this L value is also known to be positive. And this is mod f is integral mod f square, and these are also positive. So, I mean, this period integral better be with some absolute square. I was in Jacques Lewin's lecture, and I was trying to relate that maybe for adjoint L value, it is the value on the node and not, there is no absolute square there. L1 add f, there is no absolute value being taken. That is not what I am looking at. I am looking at the central critical value, which is positive, greater than or equal to 0. And it is being related to not period integrals. I mean, in his case, it was the Peterson inner product f comma f, which is a period integral. But that is positive, and the other L1 add is not positive. Okay, so anyway, this is the formalism of Ichino Ikeda, and the formalism depends on multiplicity one theorems all along. We are comparing two invariant forms, one coming from global period integral, the other coming from tensor product of local period integrals. And since there is multiplicity 1, they are related by a constant, and that constant of proportionality is an L value. So that was the conjecture of Ichino Ikeda, and sorry? No, we are always looking at L half. Sorry? L half is greater than or equal to 0. L half, no, there is no pole at 1. I have the feeling because pi 1, one of them is orthogonal, the other one is symplectic, and there is no way they can create a pole. All right, so this is something which I began last time and I just wanted to complete, and I now, so to say, change gears and start slightly different inputs which are necessary to discuss the GGP conjectures. Okay, let me just okay. So, yesterday I emphasized that to discuss any branching law, we must have a way to parameterize representations of the groups involved. So we are doing branching from one classical group to another classical group, and we must have a way to parameterize or identify representations of these groups. And the only known way to parameterize is what is called the local Langlands correspondence. So for some time, I want to discuss this. In fact, it is needed in a very precise way for GGP, and but I don't want to reach the very final precise statement without taking you along for some time. And so, okay, so maybe I will give you some first impressions of the local Langlands correspondence or theorem. So let us say G denotes a reductive periodic group, and pi G consists of isomorphism classes of irreducible admissible representations of G, and G is GF. And then there is the parameter sigma G. So I have the feeling that the Weyl group has come up many times in many lectures, but so there is this WF. Yeah, so maybe I say a few words. WF is called the Weyl group. Weyl group of a local field F. This is roughly the Galois group. If F is periodic, then not much will be lost if you confuse the Weyl group with Galois group. If F is real numbers, then it is indeed a bit different from the Galois group. And then there is this W prime F, which is WF cross SL2C. And this is called the Weyl-Deligne group. So sigma G are what are called admissible homomorphisms. Of W prime F inside the L group of G. So associated to every reductive group, there is the notion of a dual group, and then there is a notion of an L group. For some time, I will restrict myself to G equals GLN, in which case the L group is nothing but GLNC, and things will be a little more clearer. So what the local Langlands correspondence conjectures is a mapping from representations to parameters. This mapping is supposed to be surjective and finite. So, LLC proposes a map, proposes, let's say, phi from representations to parameter, which is finite to finite and surjective. So, to a representation, there is a Weyl representation, which is called the parameter of the representation. This mapping is finite, which means that several representations may have the same parameter. These representations are said to belong to an L packet. So one of the things that is very important for GGP is the notion of an L packet. So this is not the definition, but it is a property. L packet are fibers of the map P. And this is called the weak form of the local Langlands correspondence. And then there is a more precise form in which there is an identification of the two sites. So that identification is indeed crucial for the formulation of GGP. And I just want to spell out some generalities, and then I will come back to some simple examples to illustrate them. So you have pi g, and you have sigma g, and then there is this what is called enhanced Langlands parameter, enhanced Langlands parameters. And this is a disjoint union. So let's call it GI. So representations of several groups somehow are put together, and their disjoint union somehow corresponds to sigma tilde g. And okay, so first of all, let's define sigma tilde g is equal to a parameter sigma times chi, where chi is a character of the component group. Which is C sigma, and then I am looking at pi naught component group. It's a component group where C sigma consists of G belonging to G hat, which is the connected component of the L group, such that sigma W G, sigma W inverse is equal to G. So this is the centralizer of sigma. So sigma is a mapping from WF. So sigma is a parameter from WF to LG. So to a parameter, there is the centralizer, and we look at the group of connected components and a character thereof. And this is this set. And These are inner forms of a group G, and these are what are called pure inner forms, something which I will not define too precisely, but then this is a bijection. So GIs are what are called pure inner forms of a group G. Which we take to be quasi-split. I mean, I just want to spell out some generalities, and then I will just do very elementary SL2 example.
This definition, see Selmer. W runs the whole.
WF. G hat is the connected component of the L group. It's a normal subgroup. And this one is taking values in the L group. And this is conjugating elements in G hat. And one is looking at its connected component. So this is what is called the enhanced Langlands correspondence. And as a consequence of works of Jim Arthur and Moeglin, this parameterization is available for classical groups. So this is indeed the input which is necessary for stating the GGP conjectures. I am happy to clarify, repeat, but as I said, eventually I want to illustrate some of these notions in the simplest case of GL2 or SL2, so that you feel, you get a feel for what is being said. Okay, so I think one of the key words which is also said is, maybe I spell it out, the Jacquet-Langlands correspondence. Langlands correspondence. And this in the simplest case is about a representation theory of GL2F and D star, where D is the unique quaternion division algebra over F, quaternion division algebra and what the Jacquet-Langlands correspondence says is that in this notation, there is a mapping from pi D star to pi of GL2F. There is a mapping, and this mapping is injective, and its image consists of square integrable representations. So an injective map, so this is the Jacquet-Langlands correspondence. An injective mapping whose image is the set of square integrable representations of GL2F. So, yeah. So say that again.
When you restrict this map to of GI,
yes.
Is it injective?
No, no, not injective. Each one pi gi has an L packet which exists on pi gi. For SL2R, these are the discrete series, holomorphic and anti-holomorphic discrete series. And that is an example which I will use to illustrate some of these. But the way these GIs appear is through this Jackie-Langlands correspondence. I mean, there is some business of pure inner forms, etc., and the component group. So it doesn't, on the face of it, it doesn't seem to apply to this. On the face of it, this one and that one are unrelated, but the GIs are inner forms, and the way they come together is via the Jackie-Langlands. More precisely, if instead of GL2 we look at PGL2, then PGL2 has two inner forms, PGL2 and PD star. These are two pure inner forms, and the disjoint union of their representations will be related to the component group there. For PGL2, the L group is SL2, and there is a component group, plus minus 1. You see, for a discrete parameter, its image is quite irreducible, and therefore the only thing in the centralizer in SL2C is plus minus 1. So this centralizer in the case of PGL2, for which the dual group is SL2, this one is plus minus 1. And therefore, this enhancing that one is talking about will consist of a parameter sigma comma plus minus 1. And that sigma comma plus will go to PGL2, sigma comma minus 1 will go to PD star. And that's the bijection we are talking about. I mean, maybe I write it a little bit here. If G is equal to PGL2, then the dual group is SL2C. And this sigma comma chi, I'm saying is sigma comma plus minus 1, because chi is a character on the component group in SL2. And for discrete parameters, the centralizer is plus minus 1. So the characters of plus minus 1, I am also denoting by plus minus 1. And this sigma comma plus minus 1 is going to a discrete series on PGL2 corresponding to plus sign 1, and to minus sign it goes to finite dimensional on PD star. And that gives the bijection. Yeah. So in this bijection, this sigma, so you have a parameter and chi, its inverse, whatever goes to that sigma, they are related by this Jackie-Langlands correspondence. In a given pi gi, they are called an L packet. And there is a little larger packet in which an L packet lies, which is these days called the Vogel packet. So Vogel packet is a disjoint union of L packets on pure inner forms. Sorry? No, Arthur packets are different. Vogel packets are disjoint union of L packets on pure inner forms. And the GGP conjectures are about Vogan packets. So we will be looking at pure inner forms and disjoint union of L packets on them. And one of the somehow main intuition in GGP has been that this multiplicity one theorem is not only true for one representation, but it is true for the Vogan L packet. Somehow that is one of the key assertions. And I want to illustrate some of this with some examples.
So the inner forms it will belong to depending on the
Component group. Component group knows everything. Once you specify chi, it knows GI and a representation of GI. All right. So this is all quite general, and I want to maybe say a few words case of GL and F. GL and F. In this case, the local Langlands correspondence. This is a theorem due to Harris and Taylor, and also by Enyart. And this one says that this Langlands correspondence that I was talking about is an isomorphism. This is bijective. Of course, the statement cannot be as simple as just to say that these two sets are same, but these two sets are same with some properties. I mean, typical one says that the L function and epsilon factors for pairs of representations which can be defined on the two sides, they are equal. And that defines the correspondence uniquely. Of course, before I should have begun the local Langlands correspondence, I should have mentioned that the local Langlands correspondence is supposed to be a generalization of the local class field theory, which identifies the characters on WF to characters on F cross. This is just the GL1 theory. Instead of sigma G, which are n-dimensional, so sorry, this is sigma n-dimensional representations of the Weyl group. No, this is okay. So n-dimensional representations of the Weyl group are identified to representations of GL and F. That is called the local class field theory, and the local Langlands correspondence is supposed to be a non-abelian generalization of the local class field theory. And this is the Langlands correspondence to a representation. There is a Galois representation, and that Galois representation is called the parameter. One of the problems in the local Langlands correspondence for a general group is that one doesn't know how to characterize it. For GLN, there are L functions and epsilon factors, which are used to characterize the local Langlands correspondence as a unique map. And but for general reductive group, that is not there, so to say. Okay, so with this much generality, what I want to do is to do some GL2 theory and give an instance of these GGP phenomenon And so that you know at least in one simple case what is being said. I started at 55. Yeah. Yeah. All right. So okay, so maybe I say a few words about representation theory of representations of GL2F. I mean, F is periodic, let's say, then I will come to reals. F periodic. So I am talking about irreducible representations of GL2F. So these are up to twists by one-dimensional representations of the form one trivial representation. Two, these are called principal series representations. And I will denote them by PS chi1, chi2. And these are induction from B to GL2F of this character chi1 cross chi2, or maybe they are called chi1 tensor chi2. This Borel has two entries T1 comma T2, and this is chi1 T1, chi2 T2. This induction is what is called normalized induction, but I will not define what is called normalized induction. I just, yeah. Sorry? It is overflowing. And these are irreducible principal series when for chi1 upon chi2 not equal to mod plus minus 1. And if it is mod plus minus 1, then there is what is called the Steinberg representation. Which sits in the following exact sequence, which is Steinberg goes to the principal series mod x to the power half, mod x to the power minus half, the trivial representation to 0. And then the fourth, these are called supercuspidal representations. Which do not arise in, are not subquotients of principal series. So this is a rough classification of all representations of GL2, and somehow the picture is not too complicated. These supercuspidal representations can be treated mostly as a black box, and we need not worry too much for what I am going to discuss. So the Langland's parameter of PS chi1 chi2 is chi1 direct sum chi2. So this is a two-dimensional representation, and this is chi1 plus chi2, which you can treat it as a mapping from WF, abelian, which is F star, to GL2C, which is those two characters. And let's not worry too much about the Steinberg and the for supercuspidal. Supercuspidals, these are two-dimensional irreducible representations of WF. And if residue characteristic of F is not 2, then these are the representations which came up in Jacques-Lewin's talk. These are induced from WM to WF of a particular character chi. So this is the local picture, and somehow quite clean. There is analogous representation theory for GL2R or SL2R, and that is what I wish to say a few words. SL2R. So here also representations are roughly as above, roughly as for periodics. Except that there are no supercuspidals, except that there are no supercuspidals. And the real picture is more complicated in some regards, that the reducible principal series for periodics is only one of them, but here there are many reducible principal series. So except that there is this issue and there is the one, there are many more reducible principal series. Many more reducible principal series. And one says, in fact, that the principal series chi1, chi2, so following that notation, is reducible for GL2R. So for the case of GL2F, F periodic, it was only chi1 upon chi2 is not equal to this. And here the condition is that chi1 upon chi2 is not equal to t to the power n sine t. So the reducibility points are many more. And when it is reducible, it is like periodic theory. It has two components. It has two components. And one component is a finite dimensional representation, and the other component is a discrete series component. And sorry? Thank you, yeah. And when reducible, there is this exact sequence PS chi1, chi2 to finite dimensional. And then there is a discrete series pi n plus pi minus n as a representation of SL2R, and there is this exact sequence. So pi n denotes the holomorphic discrete series of SL2R whose weights for the compact torus SO2 sitting inside SL2R are e to the power I theta goes to e to the power I k theta for k greater than or equal to n, k congruent to n mod 2. So the smallest discrete series I2 is the holomorphic discrete series which has weight 2, weight 4 onwards. It misses on weight 0. So yeah. So these are called holomorphic discrete series, and then there is pi minus n, which is, so to say, pi n bar, anti-holomorphic discrete series. And the case of SL2R, pi n and pi minus n make up an L packet. So for SL2R, pi n comma pi minus n makes up an L packet. These are discrete series for n greater than or equal to 2, and there is what is called limit of discrete series for n equals 1. Modular forms of weight 1. Pi 1 comma pi minus 1. Okay. So you know, I want to use this case to do the first case, so to say, of GGP. Sorry? Sorry?
What's the associated parameter?
Parameter as a representation of the Weyl group is roughly, you know, so the Weyl group for R I did not define. WR is a non-trivial extension of Z mod 2 by C star, and parameter sigma n is supposed to be induction from C star to WR. It is like what is called the Hecke construction, and here it is Z upon Z bar raised to power n by 2. Yeah?
What happens if I1 over
No, that is good. Meaning it is not reducible. It is reducible. Algebraic in the sense that no, I mean, one is saying that only in this condition there is the two components. Otherwise, PS chi1 chi2 is an infinite dimensional irreducible representation, which is just something.
But if you take just breaking
Yeah.
something finite dimension.
No, the induced representation PS chi1 chi2, if this is not the case, is an infinite dimensional representation which has no finite dimensional quotient. What are you talking about? Algebraic?
Yes, you just take the algebraic induction.
There is nothing called algebraic induction for me. We are looking at a real group and we are looking at functions on G mod B, so to say. It's an infinite dimensional space. And the whole point of algebraic. No, you see, the thing is that there is that modulus character which has a bit of half.
That's why.
There is a bit of half there. There is some shift. It is not Borel-Weil. It is not highest weight theory. Yeah.
So in this case, finite dimensional representation
Is a quotient. Yeah.
This is a quotient, but it's still a representation.
Yeah.
Okay. So it has a after parameter. Okay.
Sorry?
Does a after parameter?
Yeah, of course. Yeah. No. Arthur parameters are available only for unitary representation. It is not a unitary representation, so it doesn't have Arthur parameterization.
So yeah, the Lagrange parameter.
Yeah, it has Lagrange parameter. Lagrange parameter for finite dimensional is direct sum of those two. Chi1 direct sum chi2 is the parameter of the finite dimensional quotient. It is the Lagrange quotient. It is direct sum of the parameters. Okay, so yeah, so I was saying that the Z by Z bar, if Z is I knew I had to explain this, then Z by Z bar is e to the power 2I theta, and therefore this n by 2 makes sense. R e to the power I theta goes to so this goes to e to the power I n theta. Square root of Z by Z bar makes sense. Okay, so what I wish to do, I still have a few minutes, I hope, and so I want to say something about tensor product of representations of SL2R. Yeah. I mean, as I said, there is notion of a pure inner form. That is the one for which the refined local Lagrange correspondence works best. And for GL2R, there is no pure inner form. And there is no component group. The component group arises only for PGL2 because then the dual group is SL2, and SL2 has a component plus minus 1. Whereas for GL2, the dual group would have been GL2, and then the centralizer is C star, and C star has no component group. So for GL2, that correspondence is there is no division algebra. GL2 sits on GL2. Just like local Lagrange for GLN.
The distinction is what you're saying is pure inner form.
Yeah, pure inner form. This is Vaughan's formulation of the local Lagrange correspondence. It is the unique place where local Lagrange correspondence is stated very precisely. And he introduced this notion of pure inner forms and the precise correspondence. Okay, so I don't want to lose too much time. We have introduced these representations pi n, and these are holomorphic discrete series or limit of discrete series pi n, which has weights going from n to infinity with a given parity. And therefore, it is not difficult to imagine that this is how it decomposes. And I want to do this not only for this pi n tensor pi m, but for all representations, so to say, in the L packet. So in the L packet, there is also pi n tensor pi minus m, and that of course will go from minus n plus m plus pi minus n plus m plus 2 plus pi minus n plus m plus 4 dot dot dot. And then there is pi n tensor pi m, and we can assume without loss of generality that one of them is bigger than or equal to this, and then we do this. So then I think you can convince yourself that these are representations. There are only finitely many discrete components to this representation. And the discrete components are pi n minus m plus pi n minus m minus 2 plus dot 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 up to either it will end at pi 2 or pi 1, depending on the parity. And similarly, there is pi minus n tensor pi m, which will begin with pi n minus m plus pi n minus m minus 2 dot dot dot, and this will begin end at pi minus 2 or minus 1, depending on the parity. So, you know, if you draw these points, these representations on the real line, as one often does, so here is the real line, and here is the point 0, here is n minus m, here it is n plus m, and then here it is m minus n, and here it is this and this. So these points are accounted for holomorphic discrete series, holomorphic tensor product. They all come with multiplicity 1 and holomorphic. And these ones are coming from anti-holomorphic. So this says these two. Then there are these ones which go from n minus m to more or less to the origin, and they go like this. So this is tensor product of holomorphic and anti-holomorphic. And there is a bit of a gap here. And this gap is from n plus m to n minus m. And you remember Clebsch-Gordon theorem from yesterday. Clebsch-Gordon theorem is theorem about tensor product for SL2C or for SU2. and it goes from n plus m to n minus m. So this is the one which is coming from finite dimensional. And the upshot is that the tensor product for SL2R together with the tensor product for SU2 makes up all representations possible. So thus tensor product for representations in an L packet of SL2R disjoint union with the tensor product for SU2 equals all representations of SL2R with multiplicity 1. Sorry, there is this parity condition. Tensor product always has a particular central character. So that is, of course, given. Jumps are 2, but that is part of what must happen. All right, so this is all for now. Thank you. Yeah, so as I said, this is one of the first cases of GGP, which I will try to explain a little further next time. The tensor product is the restriction problem. And one is saying that one is restricting from SL2 cross SL2 to the diagonal SL2. And in the process, you are able to capture all representations. No, I think the principal series is a direct integral, and that is, it depends on how you think about it. It is easier. Same picture.
Other question or comment?